So really for the next 25 minutes, 25 to 30 minutes, I just want to cover more of the digital challenges. So the capability of viewing, really using, processing, visualizing, and differences between searching and sorting. Now, from there, just going through and understanding the data interface functional requirements. Not only do you want to browse, but having comparative browsing. So we're talking later on about looking at material studies, the capability there to not just look at one study and browsing that, but doing a comparative browsing if you're looking at force degradation or stability studies. At that point, just giving some examples of really digital transformation experience. And crucially, how to process, visualize, really do identity composition, data organization. A crucial thing, you're not looking at one type of analytical technique. You'll have several differing techniques, and being able to have that information together, store it, and view it, and have that intelligent layout. As I mentioned a little earlier, just the consolidating material studies from force degradation, polymorphs, and looking at, let's say, differing genotoxic impurities or mutagenic impurities as well. And then finally, at the end, really, what's beyond characterization? The capability here of just doing some modeling, and the focus will be on accelerated predictive stability. Digital challenges. As you heard, the biggest things that we've noted is before you represent your digital twin, you really have to focus on the physical twin. In this case, designing, planning, executing your experiment. And then from there, what do you need to enable that for the digital representation? In that case, having the capability of taking in all the metadata coming from the experiment. This can be coming from an electronic notebook, a lab reactor, and the case there, once you've done the experiment, is the analysis. Like you've seen, the key capability is you're not just dealing with one instrument type. Being able to sort, have this all together in an intelligent way with the experiment makes it quite crucial to really store this information. Once you do have that storage, just having the proper layouts, depending on the user of interest and the stakeholders, where if needed, and once everything's been verified with the data and everything's been processed correctly, having this capability of accessing this data. And within this data, could be in our format, or it could just be really moved over to any type of AI, ML, DL framework. Now, how do we play a role? The crucial thing here is the capability of just taking all of these different file formats and still having the data live. Having that live analytical data with all these different techniques and having this platform where you can have those different layouts that fits the FAIR data principles of just finding, searching, and just viewing your data. Now, in this case, I'm just going to delve a little deeper into the last slide, where we're just not looking at instruments. In this case here, you could be looking at different metadata sources like electronic notebook and LIMS system, data warehouses, and being able to put that in our file format. Because once in our file format, the end user can decide what he would like to do with that. In the case of, as you've heard, really the idea would be to use one of, let's say, our APIs to take in that to any type of machine learning applications, but really the focus should be before doing that is the human access. Really an understanding of the scientific knowledge, which is still quite crucial before publishing any results and going into the master data. And really, what are the requirements when looking at that type of interface? Just having the ability to assemble and contextualize the data. Really, the identity composition is quite crucial for a user. Like I mentioned, you may be browsing one record that has multiple techniques, but doing that comparative browsing and looking in between your studies and understanding what's occurring is very important. Now from there, querying data sets using scientific data terms. Again, that sounds very simple. User goes on, he starts doing a search, he's doing metadata search, structure search, and he's doing, let's say, a relative amount search. But those are all siloed. If you're trying to do an EON number right now, currently, you could be going into your system, that software application. If you look at a structure, maybe you have a registration system, and so on with analytical data. So being able to really contextualizing this and really having it for data organization. Now, this is one of the techniques. One of the things that we love internally here is querying data with data. It's really important that, let's say, if you pull up a 1D NMR, being able to do a dereplication. Have we done this before? Have we seen this impurity? And being able to just search that so you're not duplicating work. It's just quite fundamental. And again, right now in the industry, it's one of those things that is difficult to do, especially if you have a global team. Now, once this is all completing, the ability to curate data on demand. So you have all your data, you've done all the compositions, proof of identity, being able to sort and pivot these types of views. This is quite important. You're not doing any type of transcriptions. You can then just view it, have these type of logical views as we call them, and then you can socialize this data, either by exporting as a JSON or any of the other file formats to go into these applications. Now, challenges of analytical data. This is just an interesting slide, an illustration of, let's say, a skeptical analytical chemist. Same principles as you saw earlier. They've done the planning, they've designed it, they've executed, they have the analysis, and they have their master reports. So they have all of this within one interface. They're looking through their data, but then questions may arise. Did the auto processing produce good peak integration? Those are crucial things. And if you're looking at master data that's been transferred over into other software applications, such as, let's say, Spotfire, did we miss any peaks? Were there any baseline or detector issues? And those become huge questions because for the end user, he's looking at the master data, but it's been sequenced and placed everything over that they're going to have to go back to get these answers to the lab, instrument type, CDS, such as Empower, and get a better understanding. And really, that's the query portion that becomes difficult, is understanding what occurred in that experiment. So at that point, they would, let's say, find the sample ID number or ELN number. And that just, again, just could creates a disconnect for an end user where they're just going back and forth still. So really the focus, again, on the curation aspect when you have all the data together before publishing all your results into these applications. Now, I'm just going to go through some examples of the digital transformation experience. And like I mentioned, if you're doing any type of identity composition understanding here, you'll know within our interface the ability to just take in, let's say, a 1D NMR, and crucially here, being able to have the chemical structure and linking that information together where it uses our predictive algorithm to show in green, most likely the assignment of the peaks, but also doing an automation processing to assign your peaks. And from there, having your tabular results in a view. And again, no transcription, all created on the fly. And as I mentioned, you're not just looking at that one technique. So if you're further elucidating, let's say a possible GTR or MI, the ability here just of seeing the LCMS, seeing all of the traces that were collected, all of the MS scans, and assigning the different components that you have elucidated on one interface. And that is created on the fly for the user. Now from there, having that data organization. So you'll see the data assembly within the record tree of all different types of data, but crucially, you have your chemical structure with all of your in silico properties, such as your predictions of the physical chemical properties, ADME talks, with the proof of composition, all of your data processing results, with the proof of identity, and crucially, spectral assignments, all created, all set together with the specific layout. So the assembly of data together. Now, like I mentioned about browsing, not only do you want to just browse that one record, but just imagine the scenario that you are doing any type of degradation or stability work. In those cases, you may be looking at a drug product, a drug substance, specific solution state, and you're trying to get a better understanding of all the studies that you've looked at. What, again, the software allows you to do is do that comparative browsing between records. In this case, the ability here of looking at every study that was completed and within every row, let's say the decorative of interest with all the differing numerical values. But again, not just looking at numerical values, but looking at live data, being able to overlay this. Has any peaks been missed? Is there a new degradant that we didn't account for? Having that type of view. Now, on top of this type of comparative browsing, same thing goes when you're looking at DMPK research. The ability here of just creating these type of biotransformation maps. And you'll see that later on in my talk. Really the focus within the software application is to organize things through our mapping capability. So having the metabolite map where it does a target analysis to find all the possible metabolites with all of the data in the background to really create these kinetic plots and populate these tabular results. Crucial thing, humans can really trust the results because they're not transcribing anything. They're just taking in the values and just understanding further. Now, once you've done all of this data organization, what are the common things that you may ask and want to view? And just like I mentioned with the skeptical analytical chemist, the capability here of just doing multiple searches. So a user can just go into structure, do a similarity search, substructure, etc. but at the same time do a metadata search. The capability of looking at an ELN number, sample ID, project, process, and query your results. Everything in one interface. Being able to understand what's occurring and have we seen these type of impurities or this type of compound before. And like I said, just being able to search data with data is a crucial thing. So here you can just have your carbon NMR, have your search results that shows you a similarity score. But on top of that, overlaying live data, just that capability alone. So you're making sure that you're not duplicating any work. We're not re-elucidating anything. Being able to de-replicate becomes quite important for every user, just of any organization that's trying to just handle a lot of data. Now, finally, curation on demand. Really, the things that I mentioned before of just having that data organization, having a layout that you want to view. And once you do have this layout, the ability to publish these results. This is the crucial thing, is that once you do trust all the data, you can sort, pivot, create what we call logical views. Within these logical views, then being able to socialize this data, to share that with other applications. In this case, just creating these types of JSONs that another application can digest as well. Current state of data in pharmaceutical development. So again, why is this all important? And we started doing this research, I would say, about 10 years ago, and really understanding all the different stakeholders within these differing organizations. And a good example here is if you look at the upper left-hand side with the analytical chemist. The analytical chemist may have a specific notebook, specific ability to get into instruments such as a CDS or going into NMR, LCMS, but they have access to that. Now, when they want to share that knowledge, most likely they're using something like Microsoft Office and Excel, but it's not standardized. And again, going to the other side for the process chemists, maybe they have a notebook that's specific for them. Maybe they have access to a lab reactor, again, for their cases, such as like the EasyMax. And again, open access to NMR or an LC. But when they want to share that information, again, it's not standardized. And this becomes very painful when you really need to summarize everything within the project, and especially if there's several different spreadsheets that are being used. Now, again, on top of this, if you're talking to a contract lab, this becomes even more difficult. Within that contract lab, they may have PDFs, they may have their results in a different format, and what this leads to is week-to-week meetings, trying to understand data. So again, that practice of being able to really share knowledge becomes quite crucial to collaborate. So in this portion, I just want to focus on the material challenges that we viewed and the use cases that we've seen, and specifically for degradation studies. That's the first case. So again, you have these complex characterizations, and within this complex compound, you'll see that all data is again siloed. So if I'm looking at the theoretical results or theoretical degradants, maybe that's stored in one software application. If I'm looking at analytical data, maybe it's being stored in a CDS such as Empower or Chameleon. But when we need to share knowledge, that becomes difficult. And what I mean by that is that if I'm in a team in the US and I'm talking to colleagues in the UK or Asia, it's really difficult to share that information. And really, duplicating work becomes an issue, making sure we're not all doing the same thing and looking at the same specific study. Now, this slide really highlights the degradation life cycle. It's taken earlier from a publication this year, and it goes through the whole span of the theoretical and degradant actual space. So in the case, if you look at the theoretical space, you may have, again, software that looks at the theoretical degradants. But once you reach the potential space, that capability of taking all your degradants, creating a target list, and making sure which ones are there and are not, that takes time, of course. And then finally, a likely space. If the end user is looking at accelerated predictive stability studies, being able to just outline, okay, what will happen to that degradant in about 2 to 3 years? And finally, the actual space. All the degradants all using a specific method that we found. And really, that's the space that we play in. We have the capability of taking in those theoretical degradants, taking in the potential and likely space, and having that all together to make those decisions. And how do we do that? Again, from a data organization perspective, just having a chemically intelligent platform that allows you to create these types of differing maps with live analytical data to do your comparative analysis and following those FAIR principles. And really, this next portion goes through that in more detail. So if you're looking at anything within force degradation, we just have a bird's eye view of how the studies are going. So you'll see in this image here that in the upper level, you'll have the project name of interest. Down below, once you get to the sublevels, you're looking at, let's say, the drug substance and the drug product. From there, all of the differing solution solid state experiments that you're running. And what's nice about this can be shared globally. So you get a better understanding of what's occurring for all of these studies. And how we do this is we really follow like a traffic light system. So again, for the end user, if they see anything in red, it's just an indication to them, we haven't added data, we haven't added any of our theoretical degradant information, it just hasn't started. Anything in yellow, okay, we've proceeded, we may have added some theoretical degradants, we've added some data, but we haven't finished with the completed study. Now, finally in green, what it shows to all of the users in the project team is, okay, we've completed this study. We've added all the data, we've added all the metadata as well too. Now, why is this important? This is crucial when especially you're looking through a degradant and trying to get more details. So again, right now, think, if I'm looking at a degradant or I'm looking through an impurity, how would I find it in everything within the project? It becomes difficult to manage, especially again, like I mentioned, with a global team. So in this case, imagine being able to just click on a degradant and saying, oh, we have it in 5 studies. And that's what you're seeing right now with the blue rectangles. So with that blue rectangle highlighted there in this side of the image, you'll note that these are the 5 studies that has a particular degradant. How much time does that save? Especially for end users and project teams that need these numbers right away and need to understand what's been occurring within that whole study application. Now again, the next challenge that I want to focus on is just looking at differing polymorph studies and crystalline forms as well too. And it's very similar again, if you look through it with the degradation material example that I provided. If you're doing any type of polymorph modeling, it could be using differing software applications. From there, you're executing your experiments, maybe differences in solvents and temperatures to see what happens to the form. Finally, data collection. Again, differing instrument types, I'm looking at crystallography, curved data such as XRPD, DSC, and TGA. And just like you saw with that degradation example and the DMPK example, really contextualizing this and organizing data through what we have of our map capability. Being able to see the form map. In this case, see where it's been outlined, what's occurring, but every time you click on those boxes, being able to really associate the data, viewing the data for that particular form, even the chemical structure, the drug substance of that particular form, with any PDF results, and also any details of the 3D form as well too. Now from there, other questions that may come up is, well, can I do any of the comparative browsing that you mentioned before, especially with the studies that you saw? Same techniques, that capability of just comparing differing forms and clicking any of the boxes to say, what are the differences when I look at XRPD data? So overlaying the results, getting a better understanding, and making that very easy for any members of the team and in the solid state team to really understand further what's occurring. Collaborating, sharing knowledge is the crucial thing that we've seen in really the last decade. Material challenges, really the last material challenge I'll discuss, going through nitrosamines. So in the case here, a very classic case that we saw about 5 years ago with valsartan, the capability of looking at a nitrosamine, in this case MDMA, and understanding it, where have we seen this before? Where else has this been? And this is quite crucial when you're doing this type of research. And really from the FDA, understanding what's occurring within the lab. So in the cases here too, what the software allows you to do is, again, like you saw with the maps earlier, you can have a synthetic map, a process map as we call it, and then you can say, where have we seen this? And we can change the data organization screen. So earlier what you saw was really a proof of identity. In this case, I'm looking at MDMA, and I'm looking at every record that has MDMA. So this is really the tabular result here. And when I click on that, where it has the yellow highlighted, it really previews the process map or the synthetic route with all of the impurities. So just imagine being able to see every synthetic route that has this genotoxic impurity and at every level where it carry over. So you can see the intended, unintended, and which steps or stages that it's been seen before. But on top of that, not only are you looking at the synthetic routes, you may be interested to just really understand where it is with batches or lots that you've created internally or externally as well too. So a tabular result view of every batch or lot that you've created that may have this NDMA. And above, it shows you the batch map. And again, the correspondence of saying that this batch that has this nitrosamine has been in contact with 5 other batches. How much time does that save? And that's a crucial thing for an end user, understanding this information and really this knowledge and being able to share that. Now on top, again, you can see the analytical data on the left-hand side as well too. But really, this is one of those intelligent data organizations that we allow with our layouts. Now, this may be dependent on the end user and what they're looking at, but this layout can change. So really, if I start talking to somebody more focused on the toxicological aspect of the particular compound, the layout is different. The data is still there in the lower right-hand side, but you'll see that the focus in this part is really on the metadata and also the in silico properties here. So not only are we going to see the compound name with the Inchi and SMILE strings, but a quick summary and also the in silico properties that were predicted internally within our applications or externally as well too. But sharing that all within one record. Having these types of views is quite crucial for the user. Beyond characterization. Again, as you've seen, once you have all this data, what else can you do with it? And that's crucial. This was all done automatically. I'm taking in data, I'm getting this understanding of what's occurring, but what else can we do with our data? So in this case, I wanted to focus on accelerated predictive stability, or APS. Again, it's a workflow that's been around for a long time now, and it took away from the traditional workflow that would be 2 to 3 years on looking at the stability of a compound or drug product over time to now being 2 to 3 weeks. And how we play a role is the capability, again, of taking in that metadata. So in this case, the ability in the left-hand side to take in the metadata of the temperature, relative humidity, the time of interest, and associating the analytical data. And this is all automated. And in this case here too, you're just going to note in the right-hand side, once you've added all this, it's now creating this stability map. So at every column is a differing time point. Now within every column or that differing time point, it shows you, let's say, the compound name from the peak tables. Even if you have unknowns, it will store that as either unknown or RRT, depending on what you have in your CDS system. But being able to view this as a map as the organizational piece is crucial within our application. Now, at that point, it's created this pivoted view. And remember, we didn't type anything in. There's no transcription issues. Everything was entered in manually, already processed, but all the metadata was taken in dynamically. And what you'll see here is that every row is just a differing time point. And very useful. All the rows, differing time points, and every column are the possible compound names, unknowns, all taken in right away with all of the responses or numerical values. Like I said, automatically, trusting your data is crucial here for your responses. Now, once this is completed, then you can start your modeling. Then you have trust in the data. And really in this pop-up that you're seeing in the right-hand side, the capability here of just selecting any of your degradants. So you have this drop down, you say, well, this is the degradant of interest I want to look at. And what the software is using is really a modified version of the Arrhenius calculation, and it's making those decisions and helping the user. So this is all done in the background, very dynamic. And once you reach that point, you can also see the quality of the modeling in green. And what's nice here too is that once you have trust in the modeling, you can then change those variables, change temperature, relative humidity, time. And once you've done that, that capability of seeing, okay, this degradation within 3 years, it will grow up to about 1.4, 1.5. But having that and trust in the data is quite crucial. No transcription, no entering of data, just done automatically. Okay, final piece, predictive model enablement. So what you're seeing right now is just a classic data shape diagram. And really, once you have trust in the information, it's just looking at the experiment information, experiment IDs, factors and levels, but responses. And responses are the key thing that we're looking for. So in this case, this is just a data shape diagram that's really focused on the starting materials, products, all the critical process parameters. And again, we know that stoichiometry, theoretical yield is very important, but what we really want to focus on is the responses in the right-hand side. This is the most crucial thing. And for the users, being able to view this, and right from the very beginning, like I mentioned, being able to say, is everything looking okay? Is everything correct? Because what we've noted from all of our work is, this is the rate limiting step of understanding and making sure, did we process correctly? Did we miss a peak? Do we have that complete understanding to then share and socialize this data? Because by doing that, then you have trust in the data. Because again, a lot of data scientists, well, the step where any issues do arise, it's going to be during the curation step. So having trust in this data where you can publish these results become quite crucial when you do any of the type of modeling work. Summary. So I hope that we spent some time for a better understanding of the foundational techniques and really applications within ACDLabs to allow for a digital transformation experience for material. Again, the digital twins that I really went through was the density and composition, differing material studies within the form maps, looking at degradation studies and silico properties as well too. And then finally, the predictive model enablement of just doing work, in this case, within the APS studies as well too. I'd like to say thank you for everyone's time, and I look forward to any of your questions.